Today's, oh, I'm recording now. So today's lecture notes is sort of the finishing of last time. So I have like a brief addendum to superposition of discrete and then on to continuous wave superposition. So we will start with the discrete superposition, and then we'll continue on to the continuous one. Okay, so my addendum is this. In our previous discussion, we had two side peaks, symmetric. So basically it was a 3-wave superposition. We got our wave packets out of that. So now, what if we have more? Consider 5 states. Okay, and so again, we will say central, which is like a 1/2 pi h bar e to the I p0x over h bar. And we'll say that this one has a relative amplitude of 1. Okay. And so basically, I'm not trying to say that they all have amplitudes 1, just that the relative amplitude relative to the others will be 1. Okay. And then, so this is first state. Second and third states are just like what we had in class. Which is this. I don't know why my writing goes diagonal like this, but bear with it. These ones, whoops, that's really all supposed to be in the subscript somehow. We'll say CA. And then our last bit of side peaks, which is that we can do an additional bit. So this one may be P naught plus or minus some constant times delta P. And in my original notes, I actually had an additional term in here, A, which is why this subscript gets C sub A for what it's worth. But in these terms, we would say something like B is greater than 1. Okay, so in other words, this peak is farther away than this side peak from the center. Okay, so agree, we now have 5 peaks here. We have a center, we have 2 that are separated by this delta P, and we have 2 more that are separated by some larger number times delta P. So if we wanted to do the superposition of these, our state at time 0 now looks like this. We have 1 over square root 2 pi h bar. And then essentially we have each of our peaks or side peaks in turn. E to the I P naught minus B delta P x over h bar. And then next term, C sub A E to the I P naught minus simply delta P x over h bar. And then one of this. So this is I to the P naught x over h bar. And then we get these two terms again, but with pluses here. So C sub A e to the I P naught plus delta P x over h bar, and C sub B e to the I P naught minus B delta P x over h bar. There, fit. Okay, so that's initially. In time, I may need a thinner pen nub to even fit all of this. In time, obviously we do this. We have our C sub j terms. We have our phi p sub j of x's. We have e to the minus I times ej times t over h bar. Energies being as follows. So e p naught would just be p naught squared over 2m. E p naught plus or minus delta p becomes p naught plus or minus delta p squared over 2m. And E p naught plus or minus B delta P is P naught plus or minus B. This is a B delta P squared over 2m. Okay. And obviously these ones expand to a P squared plus 2 P naught delta P plus delta P squared. And so again, we make the approximation wherein we assume these side peaks are not separated tremendously from the center. So in other words, delta P many times less than P naught, and B delta P many times less than P naught. So, you could say like delta P is 0.1 of P naught, and that satisfies things, and B is 2, and that will work. But you can't choose, say, delta P is 0.1 P naught and B is 10. That will no longer work. Okay, so with this approximation, both this term and this term will treat as approximately 0. That means that our energies are now given like so. E for P naught is unchanged. It's still just P naught squared over 2m. E of the inner pair of side peaks becomes just P naught squared plus or minus 2 P naught delta P over 2m. And then for the outer peaks, these of course are approximations. This is approximately P naught squared plus or minus 2b P naught delta P over 2m. So our time evolution for this system is not going to probably fit even with the thinner mark across here. So I'm going to have to kind of split it over a couple lines. I'm going to write this big, and then I'm going to split into 2 lines here. First of all, our main amplitude over root 1 over root 2 pi h bar. That one splits because it's all of them. Okay, and so we kind of have our upper level and our lower level. Our upper level will be maybe the first 3 terms or so. This part, there's just a lot of writing, and so, if I go silent for a period, just because there's writing without really any comment to be added to the writing. It's literally just plugging each of these things in turn. You know that it's going to be negative I ej t over h bar. So t over 2m h bar. First term's right there. Second term, c sub a, e to the I p naught plus delta p x over h bar e to the minus I times p squared. I put plus or minus over here. I just meant to put minus. Sorry. So there is a correction. It's right here is also a minus. Whoops, not x. This is the time factor. Undid a little too much there. These are p naught. It's not a p naught. There's p naught. There we go. Next term is blessedly short. Whether it fits on this line or not, I don't know. There we go. This is a T for time. This is an M and an H bar. Next line down, we have 2 more terms left. We have our second inner peak, which is messed up this thing too. There's a lot of places to have some error creep in. This one's minus, this one's the plus. This term is your P naught squared minus P naught delta P term. And then other outer peak. Not minus, this is plus. Other outer peak, C sub B e to the I P naught plus B delta P. And our time dependent phase term e to the minus I P naught squared plus B plus now 2B delta P time divided by 2mh bar. Okay. So that's your function depending on time. We can simplify it very slightly by pulling out essentially, whoops, this term right here. So if you divide everything by this term, or in other words, if you move this term out of the parenthesis, then you can rewrite this as follows. We have e to the I P naught x over h bar e to the minus I P naught squared t over 2mh bar divided by square root of 2 pi h bar. And then first term here, C sub B e to the minus I times B times delta P times x over h bar e to the minus I. And then this one would be basically 2b delta P P naught T over 2mh bar. So 2b delta P P naught T over 2mh bar. Okay, second term, C sub A e to the minus I delta P x over h bar. Yes, e to the plus I. Sorry, over here, I made this an e to the minus I. It should be an e to the plus I. Not keeping track very well of my signs here. Remember that I basically pulled this term out, and so what you're looking at in each of these is the second term, which is this minus minus for plus. I think this one's supposed to be minus. not having very good luck writing the correct signs of everything. You can imagine there's a lot of place to make algebra errors. So 2 times delta p times p naught times t over 2 mh bar, plus the only one where there's not much room to make up an algebra error. We've pulled everything out of this one, so this one's just +1. Blessed relief. Plus c sub a e to the I delta p x over h bar e to the minus I times 2 delta p e naught t over 2 mh bar, plus c sub b e to the plus I b delta p x over h bar e to the minus 2I, or I2, whatever you want to call it, b delta p p naught t over 2 mh bar. All right, so that's quite a bit. Now let's simplify the thing. Okay, and the simplification that we want is we basically kind of want to gather things with like coefficients because they will have like exponentials. So this is one of those things. And then the other one would be this set right here. Okay. Now looking at the things that are underlined in same color, e to the minus I, e to the plus I, e to the plus I, e to the minus I. We're adding them together. So that looks suspiciously like we have a cosine term. And in fact, you could combine them by doing like this. And likewise here and so on. And so if you do that, you can see that in fact, this one and this one really are e to the minus I times something plus e to the plus I times the same something, where the something is all this in parenthesis. So I'm going to knock the parenthesis back off and put it back the way it was. We can now write this below. We still have our same stuff here. And again, we can combine these as well. Essentially e to the I p naught over h bar times x minus p naught over 2m t divided by square root 2 pi h bar. And then parenthetically, if we go with the color coded parts, this one right here is basically CB. Let's go in this order. Let's put our 1 from this. The blue part looks like CA times cosine, and is times cosine of essentially delta P over H bar times X minus P0 over M times T. And then our last term, our outer terms, will look like this. And again, we have B times delta P over H bar. And then in parenthesis there, X minus P naught over M times T. So there you have it. That is what our 5-state discrete superposition will look like. Now, some comments on this, the kind of why did I do all this when we've already done the 2-state? It was not just for the fun of dragging you through, all of this math. There is a point to it. The point is this. In the 3-state superposition, we had some kind of points of interest, right? Some terms of interest. We had this term right here, and then we had a term inside of the cosine here. This right here went with phase velocity. So V phase was equal to P naught over 2M. This one right here, let's go ahead and just give it a different color instead of just triple underlining it. This one right here was our group velocity. And this matches classical particle. Now, the neat thing here is that it not only matches a classical particle, but if we look at the other term, the term that we got by adding an additional peak, we get the same value here. So we get the same group velocity term. And, I did this very arbitrarily for the 5. You could imagine trying it again with the 7. So maybe you have a B and a D term or an E, no, F, some other term, some other side peak. And you essentially get plus C sub, let's say D, cosine D delta P over H bar X minus P naught over M T. And then the next one, your next coefficient and so on. They all get different values for K, because remember that this term that I've pulled out of the thing, these right here are my K values. So this would be like K sub A. Let's go down here, K sub A. This would be my K sub B, and notice that they are not equal. Remember that K would be 2 pi over lambda. Those are not equal, but the group velocity is equal for all terms. And so all terms move together here. Okay. So that's the major point of what if we have more things in our discrete superposition. Now you could take numerical code like the one that I showed in our discussion last week, and you could ask what would happen if we had more terms, 5 terms, 7 terms, 19 terms, presumably an odd number of terms because you've got a central peak and then side peaks. I guess you could do it without a central peak as well. It's just you'd end up with a central peak that's sort of like the average of 2 given side terms. And that gets a little wonky. But that central peak is telling us what the carrier So this is going to give us our carrier value, our carrier wavelength. You could look and see what the pulses look like. And they will change from what the simulation was showing, because if you looked at the simulation that I showed, fundamentally all that changed was that the distance of these pulses got wider or narrower. So, you might have one that's like this. That's terrible. Okay, versus, and then this pattern repeats. As you add more side peaks, not just these two were basically, you know, how big is delta P? How many delta P's you have determines not only this, but also like how flat and far between pulses before the new one of these starts up. You could have one that's basically wiggling like this. And then the next one repeats, as opposed to the next one repeating here by doing so. Okay, and so that's this, you can take the simulation that I gave you and go play around with it and see what happens when there's three of these guys and so on. Okay, so let's transition from there to the very beginning, basically the setup for a continuous superposition. And all I'm going to do is the setup, because I think I'll run out of time, and then next time we'll actually do something with that that superposition, excuse me. So the setup, good grief. Setup looks like this. Um, so instead of doing a sum, up here, fundamentally, when we wanted to add together, we did a sum. If you're going to do continuous, this sum becomes an integral. Okay, so that's the first thing. And this is analogous, coming back to our result here, noting that these ended up being cosines, that in principle you could get sines and cosines. This sum is therefore a series of sines and cosines. And so we're basically going from Fourier series to Fourier transform. Okay, that's the effect that this is going to have. Okay, and we're using these right here as our base states. These are the eigenstates for momentum. You know that these are momentum eigenstates, which, as you know, are also energy eigenstates. Okay. Now our momentum, we're going to use a distribution. So we'll be doing a bunch of different amplitudes instead of discrete amplitudes. Call it continuous distribution.
Dr. Sanders,
Yes.
couldn't you treat them all as continuous? And if you had discrete states that you wanted to look at, just single them out with a Dirac delta?
Yeah. Yeah, you could. So if what you're wanting to do is start from a continuous superposition and then say, what if I have a discrete superposition? Mathematically, yes.
Yeah, you might have five Dirac deltas in your statement, but you could pull out
Right.
each discrete state that way.
Right. Right.
Okay.
With that said, you might run afoul of some uncertainty principles if you attempt to do that quantum mechanically.
Okay.
You might, your mileage may vary.
Okay.
This is what your initial state is going to end up looking like, though. So psi of x comma 0. Well, now it's this integral over all of momenta states, phi of p times var phi, as it turns out, of sub p of x dp. This phi and this phi are meant to be the same here, left off a subscript. And so these become like this. Right? Now, um, this right here is your momentum space wave function. Okay, so it's essentially giving you the amplitude of your momentum eigenstate continuum. And so if you want your time evolved state, now we have to multiply by the energy dependent phase factor. So to get from here to here, multiply by my e to the I, negative I e sub p terms. So now you end up with something like this. Well, fine, we can just write this in here.
Does it always converge?
Um, it better.
Right.
If it doesn't, then we have a problem, right? But yes, I believe that this will tend to converge. At least for the functions that we've chosen, it should. So now let's see. Now let's go ahead and put the functions themselves in. So we have, of course, this one right here is still our sort of amplitude phase. By the way, can we pick functions here that make it not converge? I suppose we can. And so in some sense, like the answer is those functions would not be valid eigenfunctions for momentum, or would not be valid momentum phase space wave functions.
Okay.
So that's, I guess, some further answer to your question. Crap, I forgot to put the amplitude. So the one nice thing about doing it this way is I need to put my amplitude in. I can just move everything over and put the amplitude in. Maybe. So we have 1 over, and your amplitude is just the familiar root 2 pi h bar. All right, so this is I p x over h bar negative I p squared. Started to write an x. It's time over 2 mh bar all dp. And of course, you can combine stuff in the exponent. And what you have is x minus et over 2m over h bar dp. All right, so this is the time-dependent generalization for a free particle Fourier transform, which, as we previously saw, is time independent for a given psi x. And so that means phi of p comma t is the time dependent version of our previous inverse transform phi p. Okay, so putting that differently, we have time independent, we have time dependent, we have Fourier transform, we have inverse Fourier transform. So basically, I'm just going to make a little grid here. Okay. So this one right here, phi of x is integral from minus infinity to infinity. Phi sub p of p e to the I px over h bar divided by root 2 pi h bar dp. The inverse and I'm actually just going to drop this subscript here at this point. Like that. Time dependent Basically looks like what we just wrote on the previous. And then this one, comment. I left off a of t in here. So let me fix that. I think that's probably as good of a stopping place as any. And I've gone a little over again. So what we'll do when we come back for the next class, and by come back, I mean Friday, um, is we will pick up with what if we have a known function for this momentum distribution. And one such known function, a very common one, is the Gaussian momentum distribution, which will make this thing converge, among other things. So that's where we'll start with the next class.
Are we meeting Friday?
Yes.
Okay.
So